Very good evening, all. My name is Ravishankar. So I'm working as an assistant professor in Department of Data Science. So it has been recently, formerly it was called Department of Statistics. So recently it has been renamed as Department of Data Science. And my today's talk is on statistical modeling of dengue incidences in, and selected climatic variables in India. So the collaborator for this paper is Kirtan Rao. So he is my student. He is a fourth semester MSc Biostatistics student, and we both belong to Department of Data Science, Manipal Academy of Higher Education, Manipal. So my area of research is basically primarily meta-analysis. So this is the first time I have ventured into infectious disease modeling. So it is my first attempt, or you can say it as a naive attempt. So any criticisms or suggestions are most welcome. So these are the contents of the my today's presentation. So a very brief introduction about dengue. So according to the World Health Organization, so dengue is considered as one of the major public health problems of the world. So as you know that dengue is of course an infectious disease, and it is a vector-borne disease. That is, it is transmitted by a mosquito called Aedes aegypti, and it is basically a dengue is caused by a virus. And dengue is seasonal, so you can see the more number of cases are observed mainly during the rainy season. And the number of dengue cases have been increasing in the recent past. So WHO fact sheet, it says that, so on an average, globally there are around 390 million cases observed. And in 2017, in India itself, there were around 188,000 dengue cases observed. So the common symptoms of dengue are fever, headache, muscle pain, joint pain, rashes, nausea, vomiting. And if you see the case fatality rate of dengue, so it has been very low. That is, the dengue does not cause death more often. Death is caused in very few number of cases, but that is the mortality or the morbidity of dengue is higher rather than the mortality. So need for the study, as I already mentioned, dengue is one of the major public health problems of the world, according to WHO. And as I mentioned that dengue is seasonal, so it is influenced by the climatic variables. So if you undertake a modeling of dengue incidence with climatic variables, so it may help to plan some adequate control measures to reduce the dengue incidence. So these are the two objectives of the study. So the first objective is to develop a model that identifies and quantifies the relationship between dengue incidences and selected climatic variables in India, and to identify the hotspots, or you can say the spatial clusters of dengue incidences in states and union territories of India. So coming to the data source. So initially we desired to collect the data on monthly dengue incidences and the selected climatic variables. So we approached NCDC, which is called National Center for Disease Control in India, and also the National Institute of Virology, which is in Pune, to collect the data on monthly dengue incidences for the states and union territories of India. And also we approached IMD, which is called India Meteorological Department, which is also in Pune, to collect the data on climatic variables. So from our literature search, we came to know that rainfall, temperature, as well as humidity are known to affect dengue. However, we couldn't get the access to all of this data. That is, we couldn't get the access to the monthly data on dengue incidence, and also the data on the monthly data on rainfall and temperature. So we could get access only to the yearly dengue incidences and annual rainfall and average temperature from the year 2008 to 2017 from www.indiastat.com. So initially we had also planned to collect the data for at least monthly data for at least 25 to 30 years, but unfortunately we couldn't get access to the data, and also we couldn't get access to the data on the humidity. So these were the data which we had. Data on yearly dengue incidences and annual rainfall and average temperature. So we could get the data for out of 29 states of India, we could get the data for 27 states. We couldn't get the data for Nagaland and Mizoram. And among the union territories, we could get the data of Delhi, Chandigarh, Lakshadweep, and Andaman and Nicobar. So total of 27 states and 4 union territories. So we had a data of 31 locations of India. So coming to the methodology, as our dependent variable or the outcome variable is a count, which is number of dengue incidences in a particular location in a year. So the ideal approach would be to use a Poisson model or a negative binomial model. So we used generalized linear mixed model. So mixed because we designated the climatic variables as a fixed effects and the states as random effect. We designated states as random effect because we can't consider that the climatic conditions will be uniform throughout the states of India. So we designated states as random effect. So our approach is generalized linear mixed model. So with states as random effect and the climatic variables as fixed effect. So this is the functional form. And we used a link function as log. That is, we used a log link function. So in alpha, it stands for a fixed effect parameters, and beta is a vector of random effects. So we used a log link function. And we carried out all the analysis in the R software. For the second methodology, it was more of a spatial analysis. So we used a technique called LISA, which is Local Indicator of Spatial Association. And we carried out this analysis in a software called Geoda. So here is more about a LISA. So LISA, it gives the extent of spatial clustering, that is how the dengue incidences or dengue cases are clustered in different locations. And this LISA is based on local Moran size. So if you see the spatial statistics, so you have a global statistic and which gives a clustering of the entire location or the location as a whole. And then there is a local statistic, so which gives a clustering of each, or you can say the sub part or the small portions of a area. So this is based on local Moran size. So it is local Moran size is also a measure of spatial autocorrelation. And this LISA, it tests the null hypothesis that there is no spatial association. That is, there is no association between the value observed at a location and the values observed at the neighboring sites. So LISA also classifies the locations as hotspots, cold spots, and spatial outliers based on the similarity with neighbors. Again, please note that it is a relative classification. So hotspots are those locations which have, with respect to dengue, with respect to this example, I can say hotspots are those locations which have high dengue incidences. Also, the neighbors have high dengue incidences. Cold spots are those locations which have low dengue incidences, and they're also surrounded by the neighbors which have low dengue incidences. And spatial outliers are those locations which have high dengue incidences, but they are surrounded by the neighbors which have low dengue incidences, and vice versa. It could be like they are surrounded with low dengue incidences, or they are the places with low dengue incidences surrounded by places with high dengue incidences. And it is a relative classification. So this is about the methodology. So let's see the result. So initially we performed a Poisson regression. So these are the results which we obtained. You can see that both the climatic variables, temperature and rainfall, are significantly associated with the dengue incidences. And this is the relative risk. Relative risk is the exponential of this estimate gives the relative risk. As we have used a log-link function, we need to take the exponential. So relative risk is a commonly used term in the, or commonly used effect measure in epidemiology. So relative risk less than 1, we can say that this particular variable or this particular factor is a protective, and a relative risk more than 1, you can say it is a risk factor or a harmful factor. Here you can see for temperature, relative risk is less than 1. So interpretation is as the temperature increases by 1 degree Celsius, so the risk of dengue reduces by 4%. That is 1 minus relative risk into 100. Similarly, for the rainfall, as the rainfall increases by 1 millimeter, the risk of dengue increases by RR minus 1 into 100, that is 2%. Okay? So this is a Poisson regression is saying rainfall is a harmful factor and temperature is a protective factor. And you can also see the confidence interval is not including a value of 1, here also, here also. So Poisson regression is saying that both of these climatic variables are significantly associated with dengue incidences. But if we check the over dispersion, so the Poisson, the main property of Poisson model is the mean should be equal to the variance. So over dispersion happens when the mean is less than a variance. So to compute over dispersion, we computed residual deviance and its degrees of freedom. So the ratio of residual deviance by its degrees of freedom, if it is more than 1, we can say that there is over dispersion. So whatever the results which the Poisson model has given is doubtful because there is over dispersion. So because of this, we went ahead and we performed a negative binomial regression. So we performed a univariate analysis wherein we included one predictor at a time. So this is a negative binomial regression with the dependent variable as a yearly dengue incidence and the independent variable as temperature. Here you can see that the negative binomial regression is showing that there is no association of the temperature with the dengue incidence. And this intra-class correlation is an estimate of a, we had designated the states as a random effect. So this intra-class correlation, which is given by the ratio of between cluster variance by sum of within cluster variance plus between cluster variance. This is between cluster variance. So ICC is given by this, and as a thumb rule, we say that ICC less than 1 as low clustering and between 0.1 to 0.19, we say it as medium. And an ICC more than 0.2, we call it as high clustering. So here we can see the ICC, which is an estimate of a random effect, is showing that there is a high clustering. And next, you can see here univariate analysis for rainfall as a predictor. Here also it is showing that there is no association between the rainfall and the dengue incidences. But it is interesting to note that both the relative risk values are more than 1. However, they are not significant. So this is a multivariable analysis or a multiple regression, what we say. So here both of the predictors have been included in the same model to get the adjusted estimates. So here also you can see that, so both of the predictors are not significantly associated with the dependent variable. And here also the estimate of random effect, it is showing that there is high clustering. So for the second objective, so this is the result of LISA. So LISA is showing that the South Indian states, namely Karnataka, Kerala and Tamil Nadu, they are the hotspots. And so all of these are not significant, whereas Bihar, Sikkim and somewhere here, you can't see, I think you need to zoom. So, and Pondicherry or Puducherry, so these are the spatial outliers. So the LISA did not find out any low or the cold spots. So coming to the, so as I said, Karnataka, Tamil Nadu and Kerala, they are the South Indian states. And we carried out this for the data of 2017, so which is the recently available data. And Bihar, Sikkim and Pondicherry were found to be the spatial outliers. So coming to the discussion, so as I already mentioned, the relative risk for both the rainfall and temperature were more than 1. However, they were not statistically significant. And from the previous studies, so they show that the dengue incidences are less in northern India because of the presence of low temperature as compared to South India. So this tallies with the result of our study also. So as our study showed that the Karnataka, Tamil Nadu and Kerala, which are the predominantly southern states, are hotspots. So strengths of the study. So this study is a unique blend of two diverse statistical concepts, which is a generalized linear mixed model and a spatial analysis. And we used a negative binomial regression so that there is the over dispersion is taken into account. And also we designated the states as random effect so that this takes into account the non-uniform spread of dengue incidences across the states of India. So limitations, as I already mentioned. So ideally, this study requires the data of monthly or the monthly data, not the yearly data. And we could get the data for only 10 years, so which is definitely not sufficient. And this could be the probable reason for getting no association of the climatic variables with the dengue incidences. And I also mentioned humidity is also one of the important climatic variable which may influence the dengue incidence. So we couldn't get the data of the humidity. Future work, yes, monthly data on dengue incidences and climatic variables could be used for the modeling. And more number of climatic variables like humidity, precipitation, so all these could be used. And more sophisticated time series modeling techniques, for instance, integer valued autoregressive model. So those time series modeling techniques could be employed to study the seasonal patterns. So I would like to acknowledge my Department of Data Science, Mahi Manipal. We also thank the organizers of DMPH for providing me an opportunity to attend the program. And I also thank ICTS for the hospitality and given to me. So these are some of the references which we have used. So thank you. So if there are any suggestions, so please, the suggestions will be taken care. Thank you.